And welcome to my Mom Teaches Tech video series on Cisco Netacad Introduction to Networks. In this video, we'll be covering my second lecture for Module 3. We're going to primarily focus on first a little bit of a comparison of the TCP IP model, which we covered in the previous lecture, to the OSI model. Here you can see the OSI model and the TCP IP model side by side. The two models that I have in this presentation, I've color coded them to help you identify how the layers match up. As you can see, the application layer is called application in both the TCP IP and the OSI models. We went through a bunch, and I mean a bunch of protocols that belong up here at the application layer. We have HTTP and HTTPS for getting information from a website using an internet browser. All of the email protocols, POP3, IMAP, SMTP. We had talked about Telnet and SSH for remote access to devices. And then we also discussed the transport layer. It matches also in the OSI model. It matches up to the TCP IP model. Can you remember the two protocols that we focused on for the transport layer? Hopefully you got them. So with the transport layer, we're talking about TCP for reliable delivery and UDP for best effort delivery. Now let's move on with memorizing a few more details about the OSI and the TCP IP model. If we stretch out the TCP IP model, you can see how these two models align a little bit better. For the OSI model, it has 7 layers, and they start here at the bottom with layer 1. Layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, and layer 7. For the internet layer of the TCP IP model, we covered several routing protocols. Those line up right here at the network layer of the OSI model. We covered EIGRP, OSPF. We didn't cover EIGRP, OSPF, and BGP, but those are routing protocols. They belong here. And also NAT, which we discussed in the last video. It also belongs here at the internet layer of the TCP IP model, which is the network layer of the OSI model. Then down here at the network access, this is where you should only list some protocols at the data link layer. So the data link layer and the physical layer of the OSI model represent just the one network access layer in the TCP IP model. When we're working with the OSI model, you'll split things out a little bit more than you would in the TCP IP model. For example, a MAC address is considered to be at the network access layer of the TCP IP model, but for the OSI model, the MAC address resides only here at the data link layer. In Cisco Netacad classes, if you're asked a question about the layer that a NIC belongs to in the OSI model, you should answer data link or layer 2. However, that's not entirely true because a NIC also handles physical transmission of data, which is down here at the physical layer. A NIC tends to fit into the TCP IP model, but often you're going to be asked a question and you'll need to represent that answer using the OSI model. If you're asked a question about cabling, such as Cat5 or Cat6, it's definitely listed down here at the physical layer, layer 1 of the OSI model. Again, in the TCP IP model, that would all belong in the network access layer with the MAC addresses. Now we're going to need to learn a few more things about the OSI model. First, you need to memorize the names of the layers. There is a mnemonic, or actually a few mnemonics, that are used to remember the names of the OSI layers. The mnemonic that I use is the one I learned from my instructor when I took my first Cisco class. And that mnemonic is please do not throw sausage pizzas away. And the idea of a mnemonic is that you can use an easily remembered phrase, and then you can take the first letter out of each word of that phrase to help you remember the names of the layers of the OSI model. Let's practice this. The first thing I'm going to do is I'll start with the numbers in the OSI model because that's the easiest. Please list your OSI model with layer 1 starting down here at the bottom. I've seen this model written the other way around, even in some excellent educational texts, but it's most accurate to write the OSI model with layer 1 at the bottom. Why? Because the OSI model and the TCP IP model are stacks. They're protocol stacks. Just like a stack of pancakes, your foundational layer or your first layer starts down at the bottom. Besides starting your numbers at the bottom, another key is that the numbers must match with the names of the layers. Once you have it numbered like this, use your mnemonic. Please do not throw sausage pizza away. And just write the first letter of each of the words on the OSI model. Hopefully, you'll then be able to just use those letters to jog your memory and write out the names of the layers. I find it easier to fill in the OSI model and then fill in the TCP IP model. Here it's easy just to copy these top 2 layers over. And here we get to the only confusing part really, which is the naming of the bottom 2 layers. At the network layer of the OSI model, remember this layer is for communicating on another network that is not your own. Sometimes when you are communicating on a network that is different from yours, that network is the internet. We can write out the word internet. And for this bottom layer, it's called the network. And then you just add the word access. So let's take a little more in-depth look at the network layer, also known as layer 3, by using a basic home network. We're going to focus here on only IPv4 for our addressing. And one of the basics for understanding IPv4 is that each device on a network must have a unique IP address within that local area network. IPv4 addresses are written in dotted decimal format. Why is it called dotted decimal format? Because this is a decimal number and these are dots. So dotted decimal. There are 4 sections of decimal numbers. The lowest number you can use in decimal notation is a 0, and the highest number you can use is 255. Notice that each of these IP addresses has a number that is unique, and that each of these addresses has a portion of the address that is the same. For every network, there's going to be a portion of the address called the network ID. It's like the name of the network. Just like if this network was a family named Smith, that's their family name. This here is the network name, 192.168.0. Then each person as an individual, they have their own individual name, like Susan, Fred. Everybody has their own name, and then they have their family name. Every device on your network has its own individual name that's listed here at the end of the IP address, and then their family name, which is the network ID. In addition to each device having the same network ID within a network and a unique identifier, you have a special location on the network, which is the way to get to another network. You could think of it as like a door to your house. You have your local network inside your house. If the Smith family wants to go visit the I don't know. My last name's Day. The Day family. They're going to have to go through their door, out of the house, leave their network, right? And go to their neighbor's house, over to their network. So when your packets are leaving your network, they need to go to the default gateway. Usually the default gateway is located on your router. Your default gateway also has a name, a unique name on your network. Here on this network, this is the name of the default gateway. If you want to get off of this network, so if you want your packets to move off of this network onto the internet, then you have to go to this location. Okay, so now we're out on the internet trying to get to our neighbor's Minecraft server. Wait, we are not out on the network with this IP address here. No, no, no. This is called a private IP address. There are specific addresses that are private addresses, and you can see them here if we do a quick Google search. You can see that we have 3 different types of private IP addresses: Class A, Class B, and Class C. This class designation was created prior to 1993. And in 1993, the class designation no longer really mattered, but we still use the same terminology, and you still must memorize. Oh, yes, memorize these private address ranges. Inside your network, you will only use an IP address designated as a private IP address. And outside your network, the internet service provider will have assigned you a public IP address. Which addresses are public? Well, the address that doesn't have another designation. The important concept that you must remember here is that private IP addresses are only for your local area network. Public addresses, which are assigned to you, are used out on the internet. We're going to say that our ISP assigned us 1.1.1 as our public IP address. So this is the address that's going to communicate out on the internet. And what happens inside the router so that your router knows where to send this packet when it returns. So here, this public IP address will be translated back and forth to your private IP address using the layer 3 protocol NAT, which stands for Network Address Translation. What do you need to know at this point in your studies? Because all of this will be covered in greater detail later. You need to know that there are IPv4 public and private addresses, and they reside at layer 3. You need to understand that the basic function of NAT is to translate the IPv4 public and private addresses so that you can have communication within your network and out on the internet. You also need to understand that each device on your network has a network ID and a unique name in the private IP address range that identifies that device on your local network. Let's talk about IPv6 a little bit. IPv6 addresses are not written in dotted decimal format. They are written in hexadecimal format. Again, we're going to cover hexadecimal, I think in the next unit here, a couple units from now. We're going to cover it in detail, but here you can see that this is how hexadecimal aligns with decimal format. We represent the decimal numbers 1 through 9 exactly the same way in hexadecimal. And when we get to 10, we represent that decimal number as an A, and then 11, a B, and so on, up to 15, which is then represented as F. Here, I have listed an example of 2 global unicast IPv6 addresses. Global unicast addresses can be thought of as being similar to a public IPv4 address in that they are routable out on the internet. Another thing that is similar is you will have a network portion and a host portion in your IPv6 address. These IPv6 global unicast addresses are in 2 separate networks, which is indicated here. The unique portion is listed here in the last 4 sections. We don't call the global unicast address a public IP address because it's an entirely different protocol. It is used for unique identification of devices. You should know that if you are using another protocol that works with IPv6, so for example, we have ICMP v4, and that's used with IPv4 addresses. And we have the ICMP v6 protocol, which is used with IPv6 addresses. And it's just slightly different. Still will have the same function. Speaking of ICMP, it's an important protocol at layer 3. So let's dive right in to ICMP protocols. The ICMP protocol sends error messages and operational information to help diagnose network issues. One ICMP tool that you will get to know very well is called ping, and it's used extensively to verify connectivity to network devices. I'll demonstrate that process here using Packet Tracer, as you can easily visualize what we're doing with this Packet Tracer diagram. In Packet Tracer, if you click on your device, you're going to be taken to this simulated desktop, and we can go to the command prompt here. So we can do ping, and we're on 192.168.0.10. We want to see if we have connectivity with 192.168.0.20. So we can use the ping utility, which is part of the ICMP-v4 protocol. And we push enter, and we are getting a reply that says we do have connectivity to this 192.168.0.20 device. There's a brief demonstration of the ICMP protocol and specifically the ping utility in action. Yay, that was fun doing a ping. That was fantastic. Now, moving down the stack to the data link layer. For now, let's take a look at MAC addresses. Here in the OSI model, the MAC address is located at the data link layer. The MAC address is used to identify devices on the local network. Remember, here at the data link layer, we're concerned with communication on our own local network. Every network interface card, NIC, it's going to be assigned its own MAC address at the factory. That's the key here. You can view the MAC address on your device. So I'm on a Windows machine here, so I can get to my Windows terminal. We're going to search here by clicking on the Windows icon and type in command to bring up a command prompt or a terminal. And then here, you're going to look at the basic network configuration and your MAC address by typing in ipconfig/all. It's a /. If you're on an Apple device running Mac OS, you can search for terminal in the spotlight and use the ifconfig command. You can see a MAC address here. When I look at the configuration of my own PC, I don't have a wired connection for this device that I'm using today, so I'm only seeing the MAC address of my wireless NIC. What you need to remember at this point, that's always the question. What do I need to remember at this point? You need to remember that a MAC address, immediate access control address, is a unique identifier assigned to a network interface card, a NIC, of a device, like your computer, a phone, or a router interface. Sometimes there's a bit of controversy about where the actual network interface card resides. Really, it's split between layer 1 and layer 2, the physical layer and the data link layer. But if you're asked a Cisco question about it, you should answer layer 2. The network medium, which for, the Wi-Fi 7 would be wireless, a Wi-Fi, that in the OSI model is moved down one layer to layer 1. Okay, now let's talk about ARP. ARP. I love ARP because it kind of sounds like a dog barking. ARP, ARP, ARP. Anyway, ARP. It's a communication protocol used to map IP addresses to MAC addresses within your local network. The reason it resides at layer 2, according to Cisco, is because its primary focus is still with the MAC address, which is at layer 2. Here's how ARP works. I'm going to give you a scenario. So you can assume computer A is a computer that needs to get information off the network. The goal is to send frames to the default gateway, 192.168.0.30. Computer A knows the default gateway address because, it's already given out as part of DHCP, which we'll discuss later, or manually set up as a static configuration. But what the computer does not know is it doesn't know the MAC address of the default gateway. And to communicate locally, we need to get to the MAC address of the default gateway. So ARP is going to take care of that. So it's going to send an ARP request on the local network that asks, who has 192.168.1.30? Tell me your MAC address. The router here recognizes its own IP address, and so it responds with an ARP reply that says, I have 192.168.1.30, and here's my MAC address. So after receiving the ARP reply, this computer, this laptop here, it stores the MAC address of the default gateway in its ARP cache. Computer A can now send any information that it wants to move off the network directly to the router's default gateway using the resolved MAC address. Now, you can look at your ARP cache from the terminal as well by typing in ARP space -A. And so if we do an ipconfig /all here on our device that's in our little network, we're going to see that we've got our IP address, and this portion is the network portion. This is the unique identifier. We also can see here that we know what our default gateway is, but we're going to need to look at, we need our ARP cache to have the default gateway resolved to the MAC address. And that MAC address is going to reside on the network interface card of the router. And if we take a look at our ARP cache, we don't have 192.168.0.30 associated with anything yet. But if we ping 192.168.0.30, then the first thing that's going to happen is there's going to be an ARP broadcast that is sent from this device that's going to end up resolving 192.168.0.30 right here. That's listed as our default gateway. And that's going to be resolved to the router NIC's MAC address. And so we'll send the ping utility. That's going to initiate the ARP protocol because we don't have this resolved yet. So it happens very quickly, and you're not really seeing it here, but now if we do an ARP-A, you'll see that we have indeed resolved the 192.168.0.30 IP address to the router network interface card's MAC address. Okay, and so hopefully this helps you to understand a little bit better about how that ARP process works. Again, you might be thinking with all this IP address talk, this seems like a layer 3 protocol. And there is some discussion about whether ARP should be at layer 2 or layer 3, but you're studying for Cisco. You know, you're in Netacad, you're studying the Cisco material. And according to Cisco, the main goal of ARP is to allow for local communication, which that is what it's for. And ARP, therefore, belongs at layer 2 of the OSI model. All right, now we're down at layer 1. So here at layer 1 of the OSI stack, this is where we're concerned about how the zeros and ones are transferred through the network. Some of our options here include copper cable, wireless transmission, and fiber optic. You know, that's all you really need to know at this point about layer 1. So that was great. Network medium. Moving on. So a couple of final associations that you need to make here with the OSI model are the way information is referred to at each layer of the stack. Data anywhere in the stack can be referred to as a protocol data unit, or PDU. Here we'll just refer to information that's coming down from the application layer 6 and 5 of the OSI model. We just refer to that as data. Because we're in networking, we're more concerned about these bottom 4 layers. So when we get to the transport layer, this is where the data stream is divided up into segments. Moving down the stack to the network layer, segments are encapsulated into packets. So data at the transport layer is called segments. Data at the network layer is called packets. And then data at the data link layer is called frames. So we have this encapsulation process that is occurring as we move down the stack. When we get to the physical layer, the information is transmitted in bits. I said that we have this specific term that we use called PDUs, protocol data units, to use as sort of a generic term for information anywhere in the stack. And I also said here that at layer 3, the proper terminology to refer to the information is as a packet. But just to make this a little more confusing, often data that's traveling through is referred to as a packet at any layer. If you're asked a Cisco question regarding what the information is called at any layer, you must remember that here at transport layer, we have segments. At the network layer, we have packets. At the data link layer, we have frames. And then at the physical layer, it's bits. You're going to have to pay attention to the context of the sentence or paragraph that people are saying or writing or using to determine, whether they're using packets as a general terminology to refer to a PDU anywhere in the stack. Where do our routers and switches belong? Well, routers are needed to get to other networks, so they belong at layer 3. Layer 2 switches work with frames, and they are used for local network communication, so they are located at the data link layer. So we've now finished covering the TCP/IP model and the OSI model, and some of the ways you need to be able to compare and contrast the two models. I hope that these past two videos were helpful in your studies for the CCNA and the Cisco NetAcad material. If you would be so kind to subscribe or like, post comments about ways you think I can improve. I'd really appreciate it. And I hope to see you in my next video. Happy studying and have a great day.